Emily Clark. She always watches my videos when she's absent and tells me when I don't put them on. And Chelsea, she watches my videos. I mean Amanda. Chelsea's her sister. Sorry. Sorry, Amanda. She graduated in Jessica McGinty's class. See, I'm that old teacher now that mixes children's names up. So how do you know if it is a lemmason with an inner loop? If the ratio of A over B is less than 1. So that means if this is smaller than this number, then you would know it's going to be this graph. Some of the questions, maybe you don't even have to graph them. You just get to tell me what type it is, right? Cardioid we've graphed before, and if you go back and look at the ones that we've graphed their cardioids, it's when A and B are the same number. So if A over B equals 1, we call that a cardioid. And I think I always leave an I out when I write the word cardioid, but I put heart-shaped here. You missed you pulling the doorstop off. Oh, I didn't know that that's where you were, though. I thought you might be somewhere else. I think page, let's see if I can make this up. 545, let's guess that. On page 545, they give you all 4 lemmason curves. I'm going to not draw pictures of those two because I'm terrible at it, but I'm going to give you the names of them because you need to know those two. I think these are the coolest one, though, because the other one is called a dimpled lemmason. And in second hour, they were telling me that it really should just be a cardioid because it looks like a cardioid, but it's not. It doesn't come in as far as a cardioid. And how do you know if it's a dimpled lemmason? That's if A over B is between 1 and 2. We can say A over B is less than 2 but bigger than 1. And so it kind of looks like this, only it doesn't come all the way in. It's like out to here. If you look in your book, page 545. Your books are supposed to be open right now to page 545, but no one's is. And then the last one is called a convex lemmason. And I call that a circle with one flat side. And that's if A over B is greater than or equal to 2, then it kind of looks like a circle with one flat side. Or probably how my circles look every time I draw them. So page 545. I should just put all 4 of those on your notes, but I like to make you look at your book sometimes. My secret plan. I think on your test, okay, I know on your test, I give you this. Like, I don't make you memorize all those. I don't know that I give you all the shapes, but I give you the names and the A over B ratio, so you don't have to worry about memorizing all the A over B stuff. Okay, but the other stuff, like the rose curves that hopefully maybe you make some connection with, and maybe the other stuff I make you learn, but this stuff I don't make you memorize all that. Okay? What else is really cool about the lemmasons? All of them are symmetric about this line. So if I was going to graph these, then 1, I know what it's supposed to look like ahead of time by looking at the equation. And 2, I know that if I pick some points up here, I can just flip them over. So it's like putting the symmetry together with the equations makes it a lot easier to graph is the idea. The rose curves, did you figure out yesterday that if you could tell how many petals there were by looking at the equation, but it was different if it was an odd number and an even number of petals? Like if it was an odd number, then whatever the number in front of with the sine or cosine would tell you that many, right? So in petals if n is odd, but 2 in petals if n was even. So we're going to look at some of them. What about between sine and cosine? Could you figure out how to tell the difference between if it was a sine or a cosine equation? Well, n is the number in front of theta. Here, let's write this out. to use A and N for a minute so I can show you, like I call this A, meaning the pedal length, and so this would be equation, we would say A times cosine of N theta. N is the number in front of theta. I put cosine there. Do you know why that one's a cosine and not a sine one? Did you get that? Has to do with the symmetry of it, I think. Or like when it's cosine, the pedal was on the x-axis, and then when it was sine, the pedal was on the y-axis, or symmetric with the y-axis. Did you notice that yesterday? Should have maybe some of that. So that's how I know this is cosine, because it's symmetric with the x-axis. In this case, what would n be? There are 5 pedals. It's odd, so that would be n would be 5. A, the number in front. Did you learn what that was yesterday? The pedal length, which is kind of hard to see this, but I think this stops at 1, which means in this case, this would be 1. So if I wanted to write the equation of this, or what if I wanted to give you on a test, give you a graph of a rose curve and ask you to write the equation, I could say that the equation for this would be 1, I don't want to put, times cosine of 5 theta. So by looking at that, I know it's cosine, so it's going to be symmetric with the x-axis. I know there's 5 pedals with a length of 1. And so the idea is that makes it a whole lot easier to graph rose curves than trying to guess the 8 million points you need to guess to get the graph of a rose curve. When it's even, look at this awesome one I found. Again, I'm just going to call this A. It's not labeled like the last one. I wrote A times, sine, I think I wrote on this one. Sine of, what would n be on this if there's 4 pedals? 2, because you double that if it was even. For even ones, I think you can, like, sine or cosine would work. Like, you could also say this was a cosine of 2 theta. And the reason being, how do you know whether you sine or cosine? It's whether it's symmetric with the x-axis or the y-axis. Do you agree for the even number of pedals, like, you get the same graph? Follow me on that? Because it's symmetric with both the x-axis and the y-axis. So you can graph sine of 2 theta or cosine of 2 theta. You get the same graph with this. Because think about the sine and cosine, they just change, like, it all works out. We're just going to go with that. Am I going to make you graph by hand something that has like 12 pedals? No. Would I maybe make you graph one with 3 or 4 pedals? Maybe. More than likely, I want you to just be able to recognize the equation or give me the equation. Okay? And actually, on your homework today, you don't even have to graph any by hand. So, what else are there? The last type of graphs are circles and lemniscates. There's some weird words in here that you never are going to ever use again outside of this class. But, you know, someday maybe you'll be watching Jeopardy when you're old and gray again. I remember that. Sometimes a circle is like the one that was 25 on the homework. Like if it just said r equals a number, then that's a circle that just traces around the circle that's on the polar graph. But you can also have circles that are not centered around the origin or the pole. And those, if this, we call this A, then we would say this is r equals A cosine theta. And this one would be r equals A sine of theta. I think it's kind of tricky because I tend to want to use the radius as A, but A is actually the diameter of the circle. And notice the difference between cosine and sine, just like the difference between cosine and sine on a rose curve. If it's cosine, then it's symmetric about the x-axis, or it's over the x-axis. And if it's sine, it's symmetric about the y-axis. So that's how you can tell which one it is. And A would be the diameter of that circle. And then this is a cool graph, kind of looks like an infinity sign, sort of. It's the easiest graph to remember, or equation to remember, because it's the only one that has r squared. and it's r squared equals a squared sine of 2 theta. So if you see any equation with r squared in it, you know it's going to be a lemniscate because it's the only one that they give you like that. And yes, this can be moved around depending on what they write, but just know if it's r squared, it's going to be this super cool graph. I believe this is a up here. So identify the shape of the graph. I want you to be as specific as possible. Don't just say a limacon. Tell me which type of limacon. Don't just tell me a circle. Tell me where the circle is, maybe what the radius or the diameter is. Don't just tell me a rose curve if it's a rose curve. Tell me how many petals it has. What's the petal length? You could even tell me if it's symmetric with the x or y axis, if that would apply to it. So be as specific as possible on these types of questions. So looking at this one, r equals 2 sine of 3 theta. What shape is it going to be if there's going to be a number in front of theta? It's the only one. A rose curve. And we can even be super specific here. How many petals is this rose curve going to have? This is the number of petals, or if it's even, it's double that, right? So we could say with 3 petals, and what's the length of each petal? Length 2. Right? So we can be pretty specific with that. We could even be specific and say if it's sine, it's going to be symmetric with the y-axis. So we would even know that. Do you have to write it on there? No, but if I asked you to graph that, you would want to know that that's true when you're picking your points. What about number 6 there? What kind of shape is it when there's a number in front, but there's not a number in front of theta? A circle, and we could say with a diameter of 8, or we could say with a radius of 4. I'm going to say radius of 4. And again, I could even say, because it's cosine, that it's symmetric with the x-axis or the polar axis. Or you could say to the left, I don't know. Like that. But again, it's supposed to help you graph these if you had to graph these. You'd have to pick a whole lot less points now that you know this stuff. And what's the one that has addition and subtraction in it? Limacon, but we want to be specific. There are 4 types of limacons. This one, A and B are the same number. So what type of limacon is it if A and B are the same number? Cardioid. So don't just say limacon there. You don't even have to say limacon at all, because it's the special type that is a cardioid that I always forget an I in it. Cardioid. And you don't even have to tell me anything else on that one, cardioid. Okay? So let's look at a couple of these graphs, and let me show you how this makes graphing a little bit easier sometimes. Just knowing the shape, I think, makes it easier, because think about the day that you had to do number 3 with that rose curve, and especially if it wasn't odd, that you just were like randomly picking points, hoping to get a shape, and you didn't really know what you were doing there. Well, let's do this one first, and then we'll go back to that one, because I feel like this one takes less work. What shape is that graph going to be? It's a rose curve with how many petals? 4 petals. How long are those petals? Length of 3, which means I think the smart thing to do is pick a point that is going to let you get where the length of that is. Or if it's 4 petals, I don't think I've ever seen a rose curve with 4 petals that wasn't here, 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 and here. Which means to me, what angle do you think we're going to pick that's going to give us that length of 3? Pi force. And so that's where I would start. In second hour, they're like, oh, you just amazingly picked the first angle right. And I said, no, not amazingly. Like, that's the point of knowing this, is that you can think about what's that going to look like and say, oh, I think if I pick pi force, I should get that length. And you can check it out that it does, because if you take 2 times pi force, you get pi halves. The sine of pi halves is 1. 1 times 3 is 3, which means I can go through there, and I don't have pi fourths on there. It's just pi 6 and pi thirds. It'll be halfway in between there. And since I know there's 4 petals, and since I know it's symmetric about the x and the y-axis, do you agree that I could go to all the force, and I could make those length of 3? And then we can pick some other points here. Like if we pick 0, I think we're going to get 0, because sine of 0 is 0, which means that's what it's going to come in there. Could we maybe pick one more point just to be really accurate? We could. Could you do a decent job of probably winging it from here? You could, but I think it's not a bad idea to pick one more point just to see, like, maybe how to go out from there. So I picked pi thirds or pi 6. Both of those are going to give us the same value here. That's why it works with sine and cosine, because when you put a 2 or a 4 in front of it, it works out to be the same thing. But if you pick pi 6, pi 6 is pi thirds. It's not so pretty. I think it's like 2.6. I just did it on my calculator because there's a square root in there. 2.6. Just to kind of give me some guidance. I didn't even pick pi thirds because I knew it was a rose curve and I knew it was going to be the same on both sides. And I just kind of use that to help me make a good graph. If you feel good, see, look, I still screwed it up. If you feel like you can make a really good one without picking a bunch of points, I'm okay with that. But I can tell you that I graphed this one way easier than I graphed number 3 on that first day of homework that we did in here. In second hour, they said, what if it was 4 theta? How would you know what to pick? Well, you'd want to pick an angle that would give you the biggest value there. You would want to pick an angle so that when you multiplied it by 4, that it would give you the sine of pi halves, because that's going to be your biggest value. So if it was a 4 theta there, would you pick pi 8ths as your first angle? Which means you'd have to just think about if this is pi 4ths, and pi 8ths would be down here. Like I said, I don't think I'm going to make you graph something with 8 petals by hand, but you could do it in a calculator. This one, I feel like I still have to pick a few points on this one, but I know the shape. What shape is that going to be? So limacon, because it's addition, it's the only one that has addition in it. And A is bigger than B, so my A over B ratio is 4 over 3. So that's bigger than 1, but less than 2. I think it's dimpled. In second hour, we spent way too much time discussing about which way would the dimple go or which way would the inner loop go. And I told them to quit stressing about it, but they couldn't. Because if you just pick the points that give you the biggest and smallest value for cosine, it's either going to have the dimple on this side or have the dimple on this side, depending on whether that's plus or minus. But for me, I just picked, not x, r and theta. I picked what gives me that max and min of cosine. So I'm going to pick 0 because I know the cosine of 0 is 1. That's going to give me 4 plus 3, which is 7. The ones that we did on our homework were a minus sign, so that's why they open to the left. But this one's positive, so that's why it's going to be over at 7. 1, 2, 3, 4, 5, 6, 7. Which tells me that it's like the picture in the book, where it's going to come around and the dimple is going to be on this side. So let's find where that dimple is. Let's pick the smallest value for cosine. What's going to give me the smallest value for cosine? Pi, because the cosine of pi is negative 1. So that's going to be 4 minus 3, which is 1. So at pi, it's a radius of 1. Now, I don't recommend that you just wing it from here. I kind of know the shape, but I think we should pick a few more points. What's super great is, like I said, all the limacons are symmetric about the polar axis or the x-axis, so I only pick positive ones, but every positive number I get to flip right down here, right? So I picked pi halves because that one's an easy angle to pick for cosine also, because what's the cosine of pi halves? 0, and 0 plus 4 is 4, so I know that's going to be up here at 4, which makes this one at 3 pi halves also at 4. And then you can pick whatever you want from here, however many points you need. I just picked a couple more. Like I picked pi thirds because I like pi thirds, because cosine of pi thirds is 1/2. And I got 5 1/2. Again, you can just use your calculator on here. I've given up you knowing what the cosine of pi thirds is. And then, I don't know, maybe you want to pick an angle over there in quadrant 2. I picked 2 pi thirds. Again, because it's negative 1/2. And so when I plug that in, I got 2.5. 2.5. And I guess I could have picked pi 6, but I didn't. I'm just going to connect it, sort of. And again, notice that it doesn't come in as far as the cardioid did. That top's much more rounder than my bottom, but that's okay. Let me try one more time. And then I'm doing that. Ah, there you go. I'm a little bit happy with that. Again, I'm not making you graph on your homework tonight. There's some matching with graphs you have to think about. There's a graphing calculator part and a no graphing calculator part of your test. On the no graphing calculator part, you definitely probably could expect to have to graph one of these, or know the shape of it at least, by looking at the equation. Okay? Questions? This is on the assignment sheet. I call this 6-5 day 2 because 6-5 day 1 we actually broke up over 2 days, but I called it A and B, and I hope you did it all in the same homework to kind of keep things together. 9 through 12, they give you 4 graphs and they ask you questions about them. So just be careful if they give you 2 equations and say which one of this has to be, explain. You don't have to write me a book on that, but make sure you understand why you're picking the right answer. 52 through 56, they want you to graph on a calculator. And then 63, 64, and 65. I'll tell you that you have like 10 minutes if you want to start 53 through 56 and graph those. Those are some weird graphs, like weird meaning that they don't fit into the categories or other ones, which they ask you a lot of questions on 53 through 56, like what's the maximum and what's this and what's that. I just want you to look at the shape of it and kind of maybe try to describe the shape of it to me of what graph that is. So if you want to do that right now, you can. If not, first few minutes of class, like as soon as you come in before the bell even rings, I'm going to be on call like saying, grab a calculator, get those graphs, because I don't want to waste 15 minutes of class tomorrow of me graphing those. Okay? So you would start on 9 through 12.